there are several general methods for doing this task. The first one and the earliest is port-based, as long as every protocol has its own port. So taking some information about the port, you can analyze the packets, and then I don't know, maybe to collect some statistics, to make some inference. However, this approach has a serious problem that there are a lot of new protocols that don't follow the rule, because in fact RTP protocol, real-time transfer protocol has could take any even port, so it doesn't go for us. The next one is a signature-based method. It exists since 2002. It's efficient, but very time-consuming, because to build valuable signatures of this method, it takes a long time to study the protocol, and maybe when the protocol changes, you should change everything. So the last one is statistical features and machine learning approach. So this one considers such features like packet size, time, EP, and so on. So we can use models of machine learning, random forests, neural networks, and so on. This approach also time-consuming, but only at the train stage, and the advantage is that it's real time or near at the inference stage. Okay, so the general stages of traffic analysis is data collection, sample processing, analysis, and inference. And yeah, of course, there are a lot of works dedicated to this topic. Most of them the works that use the third approach, machine learning and statistical features. Most of them appeared recently, several years ago. So yeah, if you are interested in, you can look at the. Okay, so in my work, I have this architecture. It's a hybrid approach to analyze the data. You can see that we have some CPU, some GPU, some GPU, NVIDIA Tesla. It's a GPU direct technology, yeah, and so on. So we are working in the bandwidth at the higher 80 gigabits per second. The main advantage is technology GPU direct, because the weak place of many solutions in this area is that we should first allocate our capture data in the CPU memory. So it really slows down the process. And also, it's this kind of architecture is well scalable. Okay, so extracted features. For the example, it's a MAC address of the machine, operation system name, screen resolution, IP address, destination IP, and much more. The important thing that we should the data should be sampled on time, because it's an analysis of time series. It was proven that any series of rhythm of traffic identification should process time series. So, and also.
Sorry for interrupting, but could you please say us about the main goal of the?
Yeah, of course, it will be next. Okay, so, yeah, the main goal of this work. You saw that there are a lot of works in this topic, yeah? So, feature. Yeah, the feature of this work that high-speed networks with bandwidths higher than 80 gigabits per second. So, if you look, there are just one, maybe two works on this topic now. And we try to study users' deviant behavior. So just imagine that yeah, at home, and one day I don't know, some robber, bad person can come to your home and use your machine. So this work is dedicated to detecting such cases. An example. Okay, so yeah, first we're collecting time series data for single user, train the model, evaluate, and try to identify deviant behavior, like addicts, suicides, terrorists, and so on. It's very useful because it's known that if we get enough data, we can describe user very exactly. You can look at the previous articles that I showed. So, yeah, about analyzing part. As long as the traffic consists two parts, encrypted and open, so we should study the encrypted part with statistical methods, as long as we cannot do anything. And then we analyze the open part with some techniques of machine learning. Of course, it will be deep learning in this case, as the state-of-the-art solutions. So, yeah, that's all. Any questions?
How you will collect data?
How will collect data? Okay. So let's back to the architecture. We have packet analyzer software. allow allows allow us to collect the data. Just a sniffer.
Mhm. So it's technically, but how it will be done juridically?
Juridically.
Yeah.
It depends. In fact, we already have some collected data
Mhm.
from the Institute of Physiology,
Yeah,
I
I know.
suppose.
Mhm.
So yeah.
Maybe somebody wants to participate in such experiments to provide their own traffic and to identify
And yeah, of course,
deviant behavior.
I should say that this architecture already done before me. So
Mhm.
it's not my work; it's just work of other people.
Mhm. Yeah,
So yeah, my part is analyzing.
And one other question about the initial data. How it is clear how we could get the traffic of, but how could we find enough of traffic of deviant behavior, and how we could label it, how we could understand that we've got some deviant behavior traffic.
Okay. So yeah, in fact, it's not the first task that I should solve in this work, because every time you should start from the easiest. Yeah. So in fact, I don't know how to exactly make this, how to collect deviant traffic, the traffic of deviant behavior. But we, but we just for solving the easy tasks like just when you want to distinguish several people, yeah, that work on one machine or several machine maybe. You can just collect data for them, and then just make something like okay, just classification, yeah,
Yeah.
that will tell you that
We discussed that with university administration, and technically it can be provided all the traffic of university, 10 gigabits per second, but uh, juridically we need to approve that students and staff of university approve that they uh, provide this data to analyze. In order to establish good experiment, we need to have not less than 50 goods. It will be 100 persons who approve that they will provide their traffic. And the first task is to identify person by the traffic.
yeah, and it could be not only the person that we used during the training,
Yeah.
because in fact you can train something like maybe autoencoder. Okay, do you know this model? Okay, just the model that tried to reproduce its own input. So, an example, when you train a set, yeah, that contains the data of several people, yeah, their traffic, we can train the encoder, autoencoder, and then when and then it will reproduce just the profiles of these people. and when there will be another person that didn't that we don't know. So
But training is anyway.
the autoencoder couldn't reconstruct the input for him. Something like this.
But anyway, you would have to have in your model to train any model. You would have to have as statistical and both statistical and structural completeness of your data, initial data. So that must be a problem.
Yeah, maybe, but it's a case of experiments because in fact I didn't make any experiments.
So what are the next tasks for you to do?
Next task for me to do is okay. I already have some collected data from Institute of Physiology. So now I just okay. So yeah, there's a problem that it wasn't sampled, and it's now it's impossible to process it with some time series algorithms. So first I will reprocess this. I should reprocess captured data and then try to build some. Of course, first a very simple model.
So pre-processing is more than half of.
Yeah. In fact,
workload.
it's 80% of the work.
Okay. So thank you. Questions?
And what we can hope to obtain from encrypted data?
Sorry.
From encrypted data,
What can we obtain? We can obtain just statistics.
like the size?
Nothing explicit like frequency. Maybe you can try to predict some distributions. Because it depends. It depends from our suggestions about the data. Yeah, of course, we can't make anything from the side of machine learning with encrypted data. But I suppose that it could be useful.
By labeling, by preprocessing data, you mean like each person works?
Not only labeling, but preprocessing data. Okay, in this case, it would be some standard procedures like normalization, scale, and so on. And of course, the most important part that we should sample our data on time with some interval.
Yeah, because there are 1 or 2 terabytes of collected data. Yeah, 2 terabytes.
Because in fact,
It is a 3 week.
now I have a data set of 4 gigabytes of data and cannot be contained in my memory.
Big data.
And yeah, of course, I think we should not use all the features. We should make some feature selection.
Okay, thank you. New day. Akilesh?
My project topic is on speech to text recognitions, which channels NLP as human does. Okay, so the main aim and main objective of my project is basically speech to text recognition. So here's what happens. First, we have the input signal, which is the audio data set, which is available. This is used for training, the initial stage. First, we need to clean the data, which removes noise from this. So we get a more clearer data set, and then we need to use something called the Fourier transformation. It is usually done to convert the audio data set into a frequency spectrum in hertz. So this is data stored in a data set called the frequency data set or the F data set. The Fourier transformation series is basically a mathematical equation which is used to sort out the noisy data from the audio data set, and at the same time it is a very fast technique. So this is the overall aim or objective of what I'm going to do here. And the first is we have an endless data set for 110 digits. We train this data set, we use this, we use it, we create a neural network, the first neural network to produce a numerical output which predicts what digit this is from 110 digit. Simultaneously, we perform data conversion. I will go deeply into this. We perform data conversion onto the frequency data set, and we produce these both to the neural network, second neural network. I will go deeply into this. First is the data conversion. Let's start with the NS data set. First, the NS data set is basically a set of numbers, handwritten numbers from 0 to 9. It consists of 55,000 training images and 5,000 validation images. So in this, basically a handwritten digit is represented in the form of an array. As you can see, it's in the form of an array. So what we do is we transform this into an image which has 28 into 28 pixels, which is a total of 784 pixels. So we get something like this. A handwritten digit, as you can see, it is a 106, number 6. After this conversion, it comes out something like this. When you represent it in the form of an array, we can see that this shape is represented in the form of numbers with regards to the intensity of the shading, which is taking place here. Now what we do is we transform this array. This is a 2D array. We transform it into a 1D array, which has a dimension 784 because 28 into 28 pixels. This is called flattening. Flattening basically ends up removing some of the 2D information, reduces its size on the database, and it gives a relationship of a pixel to the neighboring pixel, like how is its intensity, like is it light or dark. We can see it gives the relationship. And now we have the flattened data. We create a tensor. Tensor is an n-dimensional array, and we know the flattened data is 784 size, and we have 55,000 training images. So the total size of the tensor will be like 784 into 55,000. A set of 110 digits. Now we are going to use here something called one-hot encoding. One-hot encoding is nothing but if I were to pick a particular image, let's just say 4 or 1, Now this 4R1 will have a label, it will have a name, or it will have some kind of tag which is attached to it that says it's 4R1. Instead of having a name or a tag which is a string, we use an array to represent the label. This is called one-hot encoding. For example, 4 is expressed as 0000100 something till 784. Now the 1 is placed in the index position which corresponds to the number, as you can see. 4, so 0, 1, 2, 3. So in the 4th position, 1 is there, so it's a 4. So this is how we name each data. So now, after using one-hot encoding, finally we end up with something like this: 55,010. 10 is the 0 to 9 numbers, digits, and we can see that one-hot with respect to the index position. So now we have created an array of these handwritten digits. Now what we do is our input layer is basically of size 784. We produce 2 hidden layers and an output layer which is a softmax, which is to, this is basically a training section. We proceed with softmax regression, which returns a list of values between 0 and 1 that add up to 1. It is a list of probabilities. So this is one-hot true output. We given the input, output, usual, okay, but we use something called ReLU. And ReLU is used here just because we use one-hot encoding. And ReLU is basically a function, an activation function. Suppose if you give 2 numbers, it tells you which one is maximum. For example, if you give Z and 0, if Z is maximum, it's positive. If 0 is maximum, then Z is negative. That is the general structure of this ReLU function. Okay, now at the end of the day, after this digit recognition, this is our output. Like here we give the predicted and the actual. So we can see it comes to close around like more than 90% accuracy. So you can see that here it is actually 5, but it is predicted 6 here. So this is the output of the first neural network. Now after this output is done, I've given this again, let's come back to this. Now we have completed the first part of this neural network. The second part is, let's come to the audio data set. Let's come to the data conversion of the audio data set. For this we use this Fourier transformation. We divide it into frequency components. Most importantly, it tells you the proportion of each signal in your audio data set. So it tells us how much power the signal T, signal X of T, which is a function of time, has a particular frequency F. So here actually we use the Parseval's theorem. It is used in the Fourier transformation. So by being able to split signals into their constituent frequencies, one can easily block out certain frequencies by nullifying their contributions. The main advantage is that it's fast. Now, we have seen that we have made a 2D array of the numbers. We use something called flattening, a technique to transform it into a 1D array. Now we are going to use the same technique to transform this frequency spectrum into a 1D array. So now we have 2 1D arrays. Now our thing is, we have 2 1D arrays. One is for the frequency and one is for the digit. Now we are going to train these both. We are going to match these both. Now we can match the frequency of the 1D array of frequencies and the 1D array of digits. So we can match these both. So as you can see, for the second neural network, that is used to match these both. We train the frequency data set with the digits data set. This is done after training the handwritten data set to obtain the fulfillment of recognition of digits. So now we have spoken about neural network 1 and neural network 2. Neural network 1 is already present. I mean this handwritten digits recognition is already, it's a very popular example, so we know how to do it. To approach the neural network 2, which is from scratch, we need to first convert the audio spectrum into an array of suitable dimensions, as I told you before, and compare it with the digits array. We need to build a probabilistic model. At the end of the day, after these both are matched, we need to build a probabilistic model to find which corresponding digits has the highest probability with which frequency. With a given classification, this is the classification of this audio spectrum over here. It tells you which frequency lies with which type of sound. For example, like 30 to 300 hertz, it's extremely low frequency, and so on and so. If there is some kind of disturbance, a huge disturbance, distortion or something like that, we can separate it out here. We can easily separate the audio signals from noise using this. So now we have spoken about how we are going to approach the neural network 2. We are going to match this frequency with this digits recognition. So now we are going to speak about what is the use of doing this. Since it's mixed channel, which means we are going to take audio and visual at the same time. These are two different entities. After proceeding with these two neural networks, what we can do is we can extend this to video input. That is audio input plus digit input, which is visual, and we are going to convert it to text. So this is mainly useful in teaching and correcting small children in nurseries and playgroups. For example, small children are there, you tell them to go write 5, read aloud and write 5. The system can tell you whether the child is pronouncing correctly 5, or it can also tell at the same time whether he is writing 5 correctly. So this is the basic application for now. This can be extended. We can train these two with different data sets to approach with different kinds of results. This has a lot of scope actually.
If you thought about using some Google approaches or just maybe APIs for just audio recognition, audio conversion to text, because it is really working and really good results there.
Why this?
No, I mean, if you were thinking about using existing results for transferring audio to the text, or just you want to develop your own approach.
See, the thing is, we are doing mixed channels, both visual and audio. Okay, and secondly is we can use anything, not only this NS data set.
Yeah.
This is used in the initial stage to train it. Later, we can use many other data sets. We can use numbers in different languages to train the audio data set. We can do it. The whole thing is, here it's something like a universal system. Suppose I have a system here, and my camera is not working. I speak into it, still gives text. Suppose the speaker is not working with the camera, you give the visual over here, it gives the text. So it does everything simultaneously. You know, it's flexible.
Other questions? Okay, thank you again.
Will you be feeding data with missing data? You said that if the speakers, if the camera doesn't work, you can speak and it will recognize.
Yes.
This means that you should train it on the missing data.
Missing data, yeah, I understand. The thing is, we can use this system in a handicapped way. It's not necessary like the video is there, audio is not there, then visual is there. Audio alone, or the visual alone, or both.
one network for both channels, then you cannot distinguish algorithmically. Is there some missing data? Should you use some parts of your network or something? And if you're using two different networks, then it's a whole different topic. So, how to approach this problem is a question.
You mean like when missing data is there, like in our task where there were a lot of zeros?
Yeah.
Okay. This is trained with both audio and visual. I keep repeating the same thing. You can give any one of them. Any one of them. Need not necessarily be both. Can be both, any one of them. Your choice.
The idea of this approach is that one signal is coming from different sources, from visual and audio. And if we have two representations of one signal represented visually and by audio signal, that it makes neural network to work better. If you have blanks, some blanks, just visual information without audio, so you will also obtain some prediction, but if the information is enough.
So
Yes.
it's like it was said in the challenge we just spoke that the neural network will train itself to ignore the missing data.
To count if yeah, maybe not to ignore, but the task is to represent all the kind of data semantically in one space, not regarding is it visual or audio. It's nevertheless one space for
I have a question about the features you have. Yeah, it's just it's work. It's work. And it will be enough for this task.
I don't understand.
Will be enough for this task. I mean, just regular Fourier transform. It's all.
Actually, FFT, fast Fourier transformation.
Yeah. I mean, that doesn't matter just because in many tasks of audio processing, often we use more sophisticated features like
Okay.
MFCC,
yes.
and so on. Not only just Fourier.
This is the basic actually.
Okay.
This is the foundation.
What is the data features? That is,
Data features
frequencies and what else?
for this one.
Yeah.
This one is just a function of time for audio data set.
So,
We can-
will you extract the other features from the Fourier transform?
Other features in the sense?
Other features based on your transform.
Frequency and time.
Yes, of
That's
course.
enough to make a 1D array of frequency. What else do you need?
I just think that I just think that it's not enough just use the information about the Fourier transform.
Not enough information.
Yeah.
Okay.
Yeah, of course, I'm not sure.
This is just a basic. I have not started constructing yet. This is an idea. This is just a starting point.
Yeah.
Only after you code can you go in depth. What is happening? What is going on?
Okay, thank you again. Our next speaker, Sheng Leyuan. Wait. Entering flashcard, make an overload of antivirus program.
Maybe try to run test manager and do some processes. It seems like before, before was that.
Flashcard.
Double, yes. Double. Developing text-to-speech method using medical matching in the group two parts. The first is text-to-speech, and the next is using matching information. What is speech synthesis, and this is the technology that converts any text to speech, and we can call it TTS. Why we need speech synthesis, and it's very convenient. We can have some code and release our hand and more convenient result to machine, and the situations such as smart assistant, severe Google assistant, and smart speech, TV, home Excel, editing. And this is a typical TTL system. It composed two parts: the front and the back end. The front end had two main tasks. The first is convert the text containing symbol like number operations to the equivalent of the writing out words, and that the front end will assign and in foot it's called normalization or tokenization. and for the back end, it often referred to as the synthesizer to convert symbolic intuitive representation 2000. And sound is good or bad. It's relatively subjective. And so, as synthesis, we can is good or bad. We can by looking for a lot of professor people take this and one bad, two poor, three fair, and four good. Excellent. This is the popular model of speech synthesis system. The first is RemNet, and the second voice, and third is Tron. This is RemNet. This is elected carrier connections, and we can see here. This is what use this like this. It has a very large receptive field. This is the demand published last year published, and the right is also RemNet, and maybe 2 months ago published this. And this is slow. This is very fast, and this is the parallel. RemNet is faster than the original RemNet 1,000 times. This is deep voice, and contain 2 parts. And the red part is the RemNet, and the blue is the conditioning network. And there are two RDS channel QRNN and the net. Yes, that is and this is truly end-to-end learning. And for our input, we can put the one hot vector. And this is encoding. This is decoding. This is put the process net. And what is the embedded information? And for the first, this is texture, and some text is okay. And this is the information, embedded information we can read WXPTV, and this is also this. You can see this is the sky, people, and the mountain. But computer maybe not get this. This is imagine texture, and we can use the image generate some encryption. For example, like this. This means this is a group of people worked in the mountains. And how to use the image information? So the first we can take the information and the second natural capture. Information. Actually,
What is
I don't know in my phone.
Hmm?
Oh, I can try search.
so? Where is the cursor?
This video I can search in Google Net.
Okay. Press.
This is the demo of Tencent. And they choose three pictures. In the picture.
fancy video. Questions? Okay.
If there are any relations, what of existing stuff from text to speech transfer is better, and why, and how much? I mean, if you know what a WaveNet or
yeah.
I don't remember that
Yeah.
two others. One of them is better, and
Yeah.
how much? If there are some evaluations.
Yes. Here we can check them the options.
I mean, if there are some ready evaluations for one of them is better working in real situations, some statistics, I mean. It's okay, it's not actually, because it is very rare stuff.
I know. It's very
Only.
it's subjective measure, opinion score, and all WaveNet, deep voice, and one from Microsoft was measured, and one from Microsoft gained highest score. That was about 4.3 or 4.6. That is very good. So you sometimes you can't differ from human's voice.
Actually, with Google, it works as well sometimes, especially in English.
Yeah. Other questions? No? Okay. Thank you. Other speakers? Boris? Okay. So for today, that's all the speakers. My one notice for Leyuan: when you are speaking, you need to reverse to the audience and speak to the audience. That will get you better. And maybe that's all. All of you prepared good presentations and in time, and we have some discussions. That is also good. So for the next time, we plan to hear something go wrong.
You could try to open it in dark way of Chrome. Sometimes it works.
No. Okay, so we know it's Tor. Yeah, 3 persons listed.